Hello guys, so in this video I'm going to go over how to solve a Lagrange multiplier. So basically for Lagrange multipliers, basically you're given a function, a multivariable function. In this case it's 8 times x squared minus 2 times y, and we're given a constraint. The constraint being x squared plus y squared is equal to 1. And don't forget there's a plus sign in front of the x and a plus in front of the y. So now without further ado, the equation we use to solve this is we have the function of xyz is equal to lambda times the function of g xyz plus k. What's our g of xyz? Well, that would be our constraint. What's our k? Whatever constant is included with our constraint. So in this case, the k is 1. So now, without further ado, for step 1, the first thing we do is we solve for 0. So how do we do that? Well, we have the function. So we set the f of xyz function equal to lambda times gxyz. So 8x squared minus 2y is equal to lambda times x squared plus y squared. And then when we solve the constraint for 0, we move the 1 to the other side, or we subtract both sides by 1, and we're left with minus 1. Furthermore, what we do now is we subtract both sides we distribute lambda and then we subtract it by both sides. So distributing lambda, we get minus x squared minus lambda times y squared. And then since we have a negative sign in front of the 1 and we're moving it to the other side, we get plus lambda, plus 1 times lambda. And all this is equal to 0. So that was step 1. All we did was solve for 0. In step 2, what we're going to do now is we're going to find partial x, partial y, partial z, and partial lambda. In this case, we don't have to find a partial z because it's only a function of variables x and y. But for most problems, you will have x, y, and z, and maybe even other variables as well. And you'll even have multiple constraints. But in this case, we have one constraint, 2 variables. So now, without further ado, I'll keep the function visible. So our partial x, when we take the derivative of this multivariable function with respect to x, we know the negative 2y is treated as a constant, so the derivative of that is 0. However, the 8x squared, we take its derivative, and it would be 16x. Minus 2x times lambda. Where's that coming from? Well, in the equation when we solve for 0, we're taking the partial derivative of that function, not the original function anymore, because now we combine these two functions. We combine the original function of xyz and the constraint of g of xyz times lambda. So now partial y, taking the derivative of partial y, we take the derivative of the minus 2y, which is just negative 2. The derivative of 8x squared is 0. The derivative of all the other terms that don't have y on them is 0. And the derivative with the y term, which would be minus lambda times y squared, the derivative is minus 2y times lambda. And now we take the partial with respect to lambda. In doing so, the partial derivative with respect to lambda of this function is equal to minus x squared. Everywhere we see lambda, we take the derivative with respect to lambda. So minus y squared plus lambda, the derivative of lambda with respect to lambda is just 1. And now we have steps 1 and 2. So now we move on to step 3. So now that we have our partial x, partial y, and partial lambda, we move on to step 3. So for step 3, what we can actually do is we can use partial x, partial y, and partial lambda as a system of equations, and we can use these system of equations to solve for each other. So the first one we usually solve for when it comes to Lagrange multipliers is solving for lambda. And in doing so, we can use the equation from partial x. So we have 16x minus 2x lambda is equal to 0. So we can rearrange and solve for lambda using algebra. 16x over 2x is equal to lambda. Subsequently, the x's will cancel each other out, and 16 over 2 is equal to positive 8. So therefore, lambda is equal to 8. So now that we have lambda, the next step we can do is we can solve for y. So how are we going to solve for y? We can solve for y using the partial y equation. So minus 2 minus is equal to positive 2y lambda. And then furthermore, rearranging this, negative 2 divided by positive 2y, 2 lambda is equal to y. So in this next step, we can cancel out the 2's. And for lambda, we got 8. Notice how we keep the negative sign. So y is equal to negative 1/8. And all we're simply doing is just using system of equations to solve. So we have y is equal to 1/8. And now the next step is we solve for x. So how do we do that? Well, we have one remaining equation. We use the last one, the partial lambda equation. So negative x squared minus y squared plus 1. We can solve this for 1. So in doing so, 1 is equal to x squared, positive x squared plus positive y squared. And we have the value of y squared, so we know that x squared would be equal to 1 minus y squared. So x would be equal to the square root of 1 minus y squared. So therefore x is equal to 1 minus y, negative 1/8 squared. When we square the 1/8, we get a positive value because squaring will always give us a positive value. So we know that it is 1 minus 1 over 64. Furthermore, to simplify this even further, the 1 we can turn it into a fraction of 64 over 64 minus 1 over 64. So our final answer when we solve for x is equal to 60, the square root of 63 over 64. And then we take the square root of both terms and we get x is equal to positive 63 over 8. And that's our answer. So that's how we do step 3. So for step 3, all we literally did was just solve for x, y, and lambda. So now that we have done steps 1, 2, and 3, which were to solve for 0, find the partial x, y, and partial lambda, and then solve for x, y, and lambda. For step 4, what we're going to simply do is just plug in the x and y into the formula. And then our formula right here, the original function, was x squared plus 8x squared minus 2y. So now what we're going to do is we're going to place the x and y with, what was our x? Our x was positive root 63 over 8. And our y, as we did earlier, was negative 1/8. So now all we simply do is just plug in these values. In doing so, we get 8 times the square root of 63 over 8 squared minus 2 times negative 1 over 8. Furthermore, we solve it. We square the root 63, which is just 63. We square the 8, we get 64. Minus, or plus, because we have two negative signs, which is a positive sign, plus 2 over 8. And I'm going to leave it as 2 over 8. Why? Because in the next step, 8 divided by 64 is 1 over 8. So now we have a common denominator of 8. So 63 over 8 plus 2 over 8 gives us a final answer of positive 65 over 8. And that's the answer. So in quick retrospect, what did we do to solve this Lagrange multiplier? In step 1, all we did was solve for 0. We identified the constraint, which was x squared plus y squared is equal to 1. We applied the formula, which is f of xyz is equal to lambda of gxyz plus k of the function. So all we did in step 1 was identify that g of x and gxyz is equal to our constraint. We solve for 0. In doing so, in step 2, we found the partial derivative of fx, fy, and f lambda. In step 3, the first approach we did usually is we solve for lambda. Why? Because lambda is usually in every function. So we solve for lambda. Then having lambda, we solve for y. Having y, we solve for x. And that's just simple arithmetic. And from there, we plugged in x, y into the formula of the original function. And then we got our Lagrange multiplier of 65 over 8. Hello, so in this example, we have a function of x times y times z constrained by the constraint x plus 9y squared plus z squared is equal to 4. And then we have the formula for Lagrange, which is f of xyz is equal to lambda times g of xyz plus k. So now without further ado, for step 1, what we're going to do is we're going to solve this for 0 by using Lagrange, the formula for Lagrange multipliers. So right here we have x times y times z, which is our function of f of xyz is equal to lambda times g of xyz, which would just be our constraint. So x plus 9y squared plus z squared is minus 4. And now what we're going to do is we're going to distribute lambda and then bring it all to one side and set it equal to 0. So x times y times z minus lambda x minus lambda times 9y squared minus lambda times z squared plus 4 lambda is equal to 0. So that's step 1. All we did was set them equal to each other, set the f of xyz function equal to each other with the constraint. Now for step 2, we're going to find the partial derivatives of f of x, f of y, and f of z, and f of lambda, using this function that we have that's equal to 0. So partial x, the partial of x with respect to xyz would be the constant yz, minus any other x terms, minus lambda x, the derivative of that would just be lambda. Then for partial y, we are left with x times z, and then we have a y term. Everything that doesn't have y is a constant, so the derivative of those are 0, but we have the minus lambda times 9y squared, so we're left with minus 18 lambda times y. And for partial with respect to z, for the xyz would be x times y, because those are constants. And then we have a minus z squared. Minus lambda times z squared, so the derivative of that with respect to z would be minus 2 times z times lambda. And now the partial derivative with respect to lambda would be, anywhere we see lambda, we take the derivative with respect to lambda. So the derivative of lambda with respect to lambda x would be minus x minus 9y squared minus z squared plus 4. Derivative of 4 lambda with respect to lambda is just 4. So those are our partial derivatives. So now we can move on to step 3. So step 1, we solve for 0. Step 2, we took the partial with respect to x, respect to y, respect to z, and respect to lambda. And now we're going to use these partial derivatives as a system of equations to solve for x, y, z in step 3. So now that we've done steps 1 and 2, in step 1 being all we did was just solve the equation for 0. And in step 2, we found the partial with respect to x, partial y, partial z, and partial lambda. In step 3, we're going to use these partial equations as a system of equations to solve for x, y, z, and lambda. Because once we get our x, y, and z, we're going to plug it back into the main function. So now that we have that, what we're going to do now is we're going to go ahead and solve for x, y, z, and lambda. So the first thing I always like to do is when I'm doing these Lagrange multipliers is solve for lambda first. Why? Because for lambda you can just set a system of equations, and then once you set an equality for a bunch of equalities for lambda, you can always come back and reference it. So when you do the arithmetic, you get lambda is equal to x, y, or y, z from partial x, and from partial y, you get x, z divided by positive 18 times y, and from partial z, we solve for lambda, we get xy divided by 2z. So that's our equality for lambda. So now, the next step, what I'm going to do is I'm going to solve x. So what am I going to do? I will solve x in terms of y. Why? Well, the idea is I want everything, it could be in terms of z as well. But the thing is, I want everything to be in the same terms, so then I can plug it into the equation of partial lambda, and then we can solve for it. So it's just really problem solving arithmetic. So I know x from the equalities that we have set up for lambda. I know xz is equal to yz. Xz over 18z is equal to yz. And in doing so, I'm going to solve this for x. X is equal to 18 times y times z divided by z. And this is equal to, simplifying it further, 18 times y squared over z times z. We see that the z's cancel out. And for x, we're left with 18 times y squared. So that's our first value that we're going to use later on for substitution. So x is equal to 18 times y squared. Now next, I solve for z. Solve for z as well in terms of y. So now we're going to be able to substitute. So let's see. If I use yz and then the xz divided by, if I use the same equality, the z's will cancel out, so it's not going to help me. So I will instead use the last equality. X times y divided by 2z is equal to xz divided by 18y. So I'll set this equality up. Then to make the arithmetic easier, what I'm going to do now is I'm going to cross multiply. This is just algebra. I'm cross multiplying. I cancel out the x's. What am I left with? I solve this for z squared. Z squared is equal to 18 times y divided by 2 times y squared divided by 2. So now I know that the square root of z squared will give me the z value, which is equal to 18 over 2 is 9 times y squared. And I know this value in turn is equal to z, which is equal to the square root of 9 squared. The square root of 9 is 3. Square root of y squared is y. So this is our z. So now that we have our x, which is 18 times y squared, and our z, which is 3y. So now we can solve for y, and we're going to apply some substitution. So we know, I'm going to write down these equalities that we have. X is equal to 18y squared, z is equal to 3y. And now I'm going to use the last equation, the one right here we have for the partial lambda, which is minus x minus y squared minus z squared plus 4. What I can do is I can set this equation equal to 4, because remember, this is all equal to 0. So by moving it to the other side, by adding everything by plus x plus 9y squared plus z squared, I can set it equal to 4. So that's exactly what I'm going to do. And I'm going to color code my z substitution variable. I'm going to color code it in yellow, and my x1 I'm going to color code it in teal. So I know positive 4 is equal to plus x plus 9y squared, and this is from partial lambda, plus z squared. So now what I do is plus x, I'm going to substitute the x with plus 18y squared, and I'll underline it in teal, so that way you know it's a substitution going on, plus the 9y squared, no substitution needed because it's already in terms of y, and then plus z squared is equal to 3y squared. So 4 is equal to 18y squared plus 9y squared plus 9y squared. So 4 is equal to, we can factor out the y squared, and we're left with 18 plus 9, which is equal to 36y squared. Furthermore, we're going to go ahead and substitute this. 4 divided by 36 is equal to 1 over. Now that we have our y squared, all we're simply doing now is solving for y. And we're doing this through substitution. And in doing this, we get the square root of y is equal to the square root of 1 divided by the square root of 9. The square root of 1 is 1. The square root of 9 is 3. And thus our y comes out to be positive 1/3. So our x, what we're going to do here is we're going to apply the substitution, 18 times y squared, because that's the substitution that we can use for y. So in this case, now that we have our y value, our x is equal to 18 times 1 over 3 squared. And in this case, squaring the 1 we get 1, squaring the 3 we get 9. Furthermore, we can rewrite this as x is equal to 18 over 9, which is equal to 2. Thus, x is equal to 2. So how about z? So our z, if we recall, our z is equal to 3y. So z is equal to 3y. Z is equal to 3. What's our y? Our y is 1 over 3. Then, so we can rewrite this as 3 over 1 times 1 over 3. The 3's cancel out, and we're left with z is equal to 1. So now we have x, y, and z. So now that we've solved for x, y, and z, we can proceed on to step 4. So in step 4, we're going to plug in the values of the points x, y, z that we solved into the function of x, y, z. So what's our multivariable function that was given to us in the problem? Well, you should have it on your paper, but if you don't, I can reference back to it. The function that we're trying to find is x times y times z, constrained at that thing. X plus 9y squared plus z squared is equal to 4. So we're simply only focused on the x, y, z, because now that we have the points, the x, y, z points, we can just plug them into the function x times y times z. So in doing so, when we plug in the points, which I'm going to color code x in teal, y in red, and z in yellow, we know our points. We know this is the formula that we're going to use. Now we're simply going to do now is just plug in the points that we were able to come up with. So our xyz is equal to, what was our x? Our x was positive 2. Our y was positive 1/3. And our z was equal to 1. So now our function evaluated at xyz, which is positive 2 plus 1/3, and then plus 1, is equal to x times y times z. So positive 2 times positive 1/3 times positive 1. And when we simplify this, we get 2 times 1/3 times 1. And all we're doing now is simply just computing. We know the 1 won't affect the final outcome. 2 times 1/3 is equal to 2 over 3. And that's our answer for this Lagrange multiplier. So in quick retrospect, what did we do? Well, we did quite a bit of solving, but let's just quickly take you through the steps in a nutshell. So first thing we did was we were asked to find the Lagrange multiplier of this term of x times y times z constrained at that value. The first thing we did was apply the formula in the blue rectangle, which is f of xyz is equal to lambda times gxyz plus k. The first thing we do is we set up that equation and we solve for 0. In doing so, we distributed every term by lambda. We solve for 0. Once we solve for 0, we find the partial derivatives with respect to x, y, z, and lambda. We got these values. Then from here, we set up an equality for lambda. Why? Because we kept referencing it. Then we got everything to be in terms of one variable. So in this case, we selected y. We could have picked x or z. And we just used the equalities that we had for lambda to solve for x in terms of y. Then get z in terms of y. And then from there, we applied substitution. And we were able to solve for y by substituting the x and the z values in. And we got y to be positive 1/3. Then we used the equations that we came up with for y. We got x was 2, positive 2. We got z was positive 1. Then from there, we simply just plugged them into our multivariable function, x times y times z. And in doing so, we performed the arithmetic and we got 2/3 as our final answer.